run by the Wyoming National.
Morning, everybody. My name is Mark Dadden, KC0D, and I'm also with Edge of Space Sciences. I've been with the group about,
the area that we're looking at,
10 years or something. I first started out doing eye gating,
and they've told us that.
and then Marty Griffin over here roped me into driving for him. So I'm the, I call myself Alpha Junior. He's Alpha, I'm Alpha Junior, I'm driving. But then I got more interested in this, and one of the things that we found over time was that we were always heard about this thing called post-burst chaos, and somebody else mentioned it this morning. And I was trying to figure out, what actually causes this thing. So you can go to the next one here. This is, I took the text off the slide so you can see this. So this was a snapshot of I think they had a high-definition camera pointing up and caught one frame right at the burst. But one thing that fascinated me about this is, you look right in here, it looks like the balloon shards are actually eating the parachute. And I go, okay. But we also had some other things going on. And we'd always come back where this sort of define post-burst chaos is, we end up with these issues with the balloon coming around, with the payloads wrapped around the shroud lines, the parachute, and then, Steve. And then we talked about the antennas being broken off. So we had, this probably isn't the best solution here, but that one's broken off. I don't know if you can tell here, but that used to be an antenna. It's just completely gone. And I pulled these pictures out of our EOSS archives, and there's a bunch of them. This one came back with the balloon shards wrapped around. This is actually the first payload. Here's the spreader ring, parachutes down here, and here's the whole balloon here wrapped around the middle. Now you'd think that if this thing, the payload is going down, the balloon's supposedly going up, you wouldn't expect the balloon to be around the middle of the flight string. So something else going on here. We've also noticed at times we lose GPS lock at first, which usually means that something happened, like the GPS goes upside down or does something weird. This particular one, we had the flight line all wrapped around the antenna. I don't know if you can tell here. You guys are all nodding your head. You've seen this stuff. Okay, Steve. We know that this happened right after burst. We know that if you cut it down gracefully, you don't see this. It comes down nice. I was just looking at a video the other day that I think one of you posted. Had a really nice shot of the, I think it actually burst, and the thing just went, wow, it just fell down slowly. That's beautiful. But sometimes we see it, sometimes we don't. And we don't know really why some flights have it, some flights don't. But some of the things that we've done to try to minimize it, for instance, we've put a long flight line between the parachute and first payload.
What do you define long?
See, what would you say?
40 feet sometimes.
Wow.
Yeah, so we fly some pretty long payload strings. I'm going to show you here in a minute. The payload that I have is flown on the couple. I'm usually near the bottom. I'm probably like 70 feet or something down the flight string, so it's pretty exciting at the bottom. Go ahead, Steve. So one of the things that I said, okay, let's see if we can determine what's going on during this post-burst chaos. How do we measure this? How do we look at what's going on? It's kind of hard to see through the ground. And then I said, well, in order to do that, what other kinds of things could I do to be kind of exciting? So I got into this logging external temperature, and what started that is we were out on I was with Marty, we were out there picking up a balloon, and there was a little grade school girl that was out there, and at the time they were flying crickets. I guess we're not flying live animals anymore, but they flew some crickets, and they came back kind of dead looking. It turns out they weren't dead. It's kind of harder than that to kill crickets. Never feet in the air, but she asked me, she says, how cold did it get? I don't know. Real cold. We didn't really have any real data that would say, how cold was it. So I said, well, how come we couldn't tell them? Why not? So I got interested in that. Also, barometric altitude. We've been flying a barometer for some time, but we always got this data that was kind of weird. It was sort of a A to D data, an 8-bit A to D, and it came back and had real coarse. And you'd ask Nick, so what's the altitude look like? If run his calculator real quick and say, well, it looks like it's about there. And then we found out that 8 bits really isn't enough when you're looking at 100,000 feet and with 8 bits, it's not real good. So anyway, I decided, okay, let's see what we do about that. Of course, logging a bunch of data. Digipeater, we like to fly those because we have a bunch of trackers out there. It's really nice to be able to see where the other people are as you're out there looking at that. I noticed too that it'd be really nice to know when the balloon burst. We'll typically look at track point. Nick's track point will give us, he looks at GPS altitude. If he looks at a couple sequential data where it's falling, he says, well, that's probably burst. But that could be a minute or more after burst, so it falls a long way in a minute. I said, maybe there's some way I can figure out how to detect a burst. And then the tracking tone. Every once in a while, these things fall in a cornfield or someplace. It's the way they hang out there. You'd like to be able to turn on tracking tone, but I don't really want to have it going all the time because A, it's kind of annoying, and B, it wastes power. And you don't really need it on the way up. So I'll see if I can turn that on. Things like responded DTMF codes, be able to cut it down, and a bunch of other things, like you'd be able to turn on the tracking tone, turn off the tracking tone, those kinds of things. Also, thanks to some of Ned's advice, we reconfigure the payload quickly or remotely. One of the things we found that causes problems with getting air into the payloads is continually opening and closing the payloads. You've got to open it up, charge the batteries, close it back up. You've got to open it up, change the frequency. Okay, you're sitting out someplace, and, oh, I got to do this, oh, I got to do that, and it's like, well, can we do this remotely without having to open the payload up? So I took all these things and said, I wonder if I can do some of that. Let me see how close I came. So what I'm going to go through now is I'm going to kind of walk through the various different pieces of the things I've got on this payload, and then at the end we'll see how I did. Okay, Steve. So the first thing I'm going to introduce is some concepts. How many of you in here are pilots? Oh, good. I just want to know who I can have give me the answers to these. If I've got to call for help on some of these, I'm not a pilot.
Did you qualify with how many of you are good pilots?
Yeah. Well, you're here.
A good pilot is one with an equal number of takeoffs and landings.
So you're evidently a good pilot. So for the rest of you, there's a thing called an inertial measurement unit, or we'll call it IMU from here on. We'll call it IMU. And what that thing is it's got an accelerometer, a 3D accelerometer in terms of that's just a G meter. So it goes, X, Y, and Z axes. A gyro, it gives you the rate of change, so how quickly you're turning. And then a magnetometer, so that's basically a compass sort of thing. It says, okay, what is the magnetic strength in all the different axes? See? And then there's a thing called the fusion algorithm. So what that does is that takes this data and produces what they call yaw, pitch, and roll. So for the pilots, you're all familiar with that. And then Steve, go ahead and click it again. Which one of this should animate over here if you keep going. And so what these yaw, pitch, and roll basically, so the roll, is this way. The yaw, here, back up one. And I guess that's not working. Okay, so the yaw goes this way, and the pitch goes this way. Okay? And so by using this data, you can fuse it all together and you get this information. Now one thing that can happen is something called Gimbal Lock. And this is kind of interesting because if you take a circle and you kind of put these hoops in the different axes, so you end up with yaw, pitch, and roll all going these different directions. If you end up being in the airplane and you end up going into a very steep climb, I think you have to be an F-16 to do that. Not your Cessna, little Cessna. But what happens is, Steve, go ahead and put the next one. And what it means when you get down here, it's called Gimbal Lock, is what happens is two of your flight control surfaces do the same thing. And that's not good. So what happens is, in this case, your ailerons and your rudder actually interfere. They kind of can do the same thing, so that you can lose control of the aircraft. Go ahead. An example of that is if you're standing on the North Pole, and someone says, look east. There is no east. There's only south, really. You're standing up there, okay, that's one way. It's not this way, it's not that. That's south, that's south, that's south, that's south. And so that's an example of what Gimbal Lock looks like. Next one, Steve. And a couple of examples. Go ahead. So in animations, one thing that can happen is you get this sort of weird behavior. And I'm going to show a video clip here in a second of what I observed. And I hadn't really thought about this when I started doing this, but when I looked at the the animation I got there, I go, something's really weird going on here. But this is a real thing because what happened in Apollo 11 and nearly in Apollo 13 is they had this happen on the spacecraft because they actually used these same things in the spacecraft, the mechanical version of this. And you can very quickly lose control of the aircraft, and they almost did. In Apollo 11, they wanted to land on the moon. That nearly happened. Apollo 13, when they had the explosion, it caused the aircraft to kind of go weird, go in all these dimensions. So far, they nearly had it happen. Sort of like a post-chaos burst, kind of goes like all of this kind of stuff. Got it, Steve? So in a minute, and the next slide, I'm going to show you an animation, but I want to describe what you're going to see. So what I've taken is I've taken the yaw pitch and roll information for this IMU that we have. And I then play it back in real time. And over here, so this is the payload, the tink thing, which looks like this thing over here on the table. And the arrow, if will point north. Up is up. This would be east. This would be down. And then this is the altitude in feet per minute over here. Then the acceleration, x, y, and z. So the reason you see this one pointing up is because we've got a positive, almost 1g acceleration. So if you take all of these, they should add up to about 1.
Mark, is this real-time data?
This will be real-time data. Yes, this will be real-time data. Then we've got the yaw pitch and roll information over here. So now you can see it's pointing sort of south-southwest, which is this way. And it's pitched to pitched to the right, or I guess that'd be the left 3 degrees. And roll, it's actually down 5 degrees. Okay? Kind of oriented there. Okay, Steve, why don't you click the next slide and let's see if that starts. You may have to click the bottom of the screen and see if the animation will start. There you go. Okay, so now we're going to be at 100,000 feet, and we're within a few seconds of burst. So it's just calmly swinging around, checking out the sights. And here in a second, you'll see you kind of look over here at the altitude. Okay, you can see just what happened as we hit burst, and so things are getting a little bit more exciting. Now, what you see that is Gimbal Lock. Okay, you saw that rapid flipping up and down. That's the Gimbal Lock problem as it hit the vertical. But most of this is real. And so you start looking at this thing, and I think when I looked at this about 100 times, at one point right there, it spins about 6 times in a complete circle real quick. And you wonder how an antenna gets ripped off. There you go. There you go. Yeah, maybe it was more than 6.
No air yet. Parachute doesn't make any difference.
Well, it should be more of a drag a little bit soon. What's the altitude?
92,000 over here. Yeah.
So how far from the parachute did this fly? Do you remember?
Yeah, it's about 70 feet. It's near the bottom.
Yeah.
Wow.
I've got a couple of these. So I'll show you this one. And what I'll do is, in the interest of time, I won't repeat this now. But if anybody wants to take another look at this later, I can do it during the break or whatever. I've got it on my laptop.
Put it on YouTube.
On YouTube, that's the idea.
Was this data transmitted live, or did you record it?
I recorded it. So it's recorded at 50 hertz rate for 20 samples per second. And it's recorded to an SD card. And then when I got it back, I got the data and then I decompress it and then play it through through the software that it does the animation. So we're getting.
I want to throw up after
So this is getting close to the end. I'm not gonna, you could actually watch the whole flight if you wanted to, but you can sit there for an hour and a half and watch it. But most of it's fairly boring until you get around the burst. But you can see that even, and what I found in both of these was this flight payload's only flown twice. The other one isn't quite as exciting as this, and I don't know why this one is more exciting than the other, but it's pretty exciting all the way down. I mean, what we see is a fair amount of motion on this, and a fair amount of flipping, and rotating around, but you can see it's calming down a little bit more now than it was earlier.
But you're also still at 12,000 tons lower, is that?
Yeah, but much lower, yeah, because we're down to 82,000 feet now.
Mark, does this catch the swinging as we come down through the lower atmosphere?
Yes, and I've actually got an example of that. Okay, Steve, why don't you go to the next one?
Have you tried making it more aerodynamic than square to see if that helps?
I haven't yet.
Bullet shape?
Yeah, there's another thing that I did too, is the batteries, the center of gravity is fairly high because where the batteries are located in there, so they're actually above the center, they're not located at the bottom. So that probably makes things a little worse by having that. So I haven't played with tweaking some of these things. So one of the things is, okay, how do we get around this gimbal lock issue, some of that quick flipping that you saw? Well, there's another way of doing things other than using the Euler angles. And these are called quaternions. And you probably, if you're into 3D animations or whatever, you've heard of that. These avoid the issue. The nice thing about this particular IMU that I'm using, it'll give you both. And I wish on the first slide I had kept the quaternion data because you can take it later on and do whatever you want to with it. Once you have your Euler angles, you're sort of hosed. I mean, that's what you've got. So you can convert back from that. And what the quaternions are, they're 4 unitless numbers between 0 and 1. And they come out in their scale. Okay, so then I have to divide by 2 to the minus 12th and get the actual number. But this is how you get the raw pitch and roll out of the quaternion data. And that probably something I want to do live in a little 8-bit processor, but I actually do. For at a lower rate. Go ahead. Thank you. Go ahead, next one. Okay, so this one I'm going to run. This is the second flight. So this one we're going to run. And I used the quaternion on this one and did the conversion afterwards. But you'll still see that there's still a couple issues in here, but it's not nearly as bad. So go ahead. I think go ahead and start it. And this flight didn't go quite as high. Now let's start here eventually. And so this one actually, this is a student flight, so it's 73,000 feet. Really doesn't want to start, does it? Well, somebody running Office 2007, I did this in Office 2016. Well, there you go. Okay, Parker, why don't we just I'll come back to that one. Why don't you just go to the next one? So that one is very much the same, except what you'll see is it didn't flip around as much. Okay, but there was still a couple issues in it. When I went back and looked at the data, this is still sort of working in progress.
Same payload?
Same payload. Yeah, different flight, same payload. And I found that there's still an issue in here. When I started, when you're doing this stuff, Google's your friend. I mean, really. So what I found out is there's if you convert back to the Euler angles, you still have the same issue. And so there's 6 different orientations you need to handle manually. And those are mostly pointing up and pointing down. And there's a link down here if you're really interested. Down this EuclideanSpace.com talks exactly about this issue, which ones you have to watch out for. And so I need to go back and do that. So I still, I just plotted on here the Euler angles, and then what the the quaternion values, and then what the Euler angles were. And you can see there's a couple step functions in here that aren't right. You shouldn't just be stepping like that, like 100 degrees or something like that. It should be more smooth like this. So I've still got a little bit more work to do to figure out exactly what's going on there. So this is what the board looks like. The IMU is this little part right here. And then I blew it up so you can see what it looks like. It's really a nasty part to try to put in our book. It's got 0.5 mil spacing. So this is it. It's made by Bosch. The nice thing about this one is you can do a lot of this yourself. So you can buy a board that has the sensors on it, and then you can do the fusion algorithm yourself. And I started out doing that. You can start out by doing the math and the processor and all that. But for about $8, it's nice just to be able to have this one. You can also buy the breakout board for this from like Adafruit. so you don't have to try to solder this thing onto the board. But if you use this one, it's nice because it'll output the other angles and the quaternions directly, as well as you can have direct access to the accelerometers and so forth directly in there, which is what I did on the animation I showed. I was just reading the accelerometer out of there. As I mentioned, I output it to the SD card at 50 hertz, and then I actually do the math on the little 8-bit processor and output it real time to a serial port to be able to do some testing with it and the math and so forth. And I am set up to do that. Maybe at the break or something, I'll set that up so you can take the payload over here and you can play with it and see what it is in real time. Now the other thing I use the accelerometer for is, one of my things on the would be nice list would be able to measure burst. How do I determine burst? I came up with this idea as well. I think it'd have a period of 0 Gs. As soon as the balloon bursts, I should see 0 Gs for a period of time. So I took the payload, got on the roof of my house, and dropped the thing. And, I did see a 0 Gs for a period of time. I said, okay, let's try that. And I've got some data here to show you what the looks like after burst to be able to detect that. Okay, we talked about external temperature. And there's a couple things you need to be able to do. Number one, it's kind of hard to do. We've tried it before several different times and we've had problems doing it. One of the problems is everything radiates heat. So you've got to have a sensor that's out of the sun, stays out of the sun, but it's got to be in the airstream. And you have a payload that's doing, spinning around and all this stuff. So that, to me, that eliminated everything but the bottom in order to stick it out the bottom. It can't self-heat. It needs to respond quickly, so you can't have something that's going to be some sort of sensor that's going to heat itself up. It should have low thermal mass because you want it to respond fairly quickly. The nice thing about thermocouples is they're really small. So the sensing end of it's just that piece of wire right there. And they respond all the way down to 330 degrees F. On the low side, and that's like 1,700 degrees or something on the high side. So, plenty of range for what we're doing. They generate microvolts, and that is converted to temperature. And the nice thing is there's a chip that does that. You don't have to try to read microvolts. The other way to do it is with these one-wire temperature sensors. I know a lot of people have used these, and they're the Maxim, the DS18B20s, and so. I didn't really know which one was going to work better, so I said, okay, let's try both. And so I've got some data on here comparing one against the other. Now, these are not rated below -67. I think that's kind of pushing it for those. The accuracy is about the same. Below 14F, the accuracy falls to 3.5, which is the same as the thermocouple. The way these things actually measure temperature, now it's got some electronics in there, so it has that issue of possible self-heating. I don't know how much that is. But the way they measure temperature is you've got to get these leads, these metal leads right here, out into the temperature because it conducts the temperature into the chip, which actually does the measurement inside this little plastic package. And this is the same old little transistor, like 222 that everybody's used. Okay? And so what I found is, I'm not quite there yet because I found that, as Nick's showing over here, he's holding up the payload, this payload. And in the bottom, there's a hole in the bottom of the payload, a little square hole there. And those two sensors are in there. We found that on the way up, that actually holds a little warm air pocket in there. So the last flight I flew, I put some straws through the sides. Said, well, maybe I can provide some airflow to it, but it still wasn't enough. And I think the payload's also warm. It's hard to get something down to -60, before you launch it. So we're still getting there, but on descent, it seems to do pretty well because you've got a pretty good airstream coming through this thing on the way down. And so what we're looking at here is the gray one here is let's see, that's the internal temperature. So that's inside the payload. This one is the GPS altitude. Okay, this is the feet, K feet over here. This is the temperature over here in degrees F. And the yellow one is let's see which one's which. The orange one is the external thermocouple. So that's the thermocouple, and there's the one wire. And you can see the one wire is reading a little bit warmer. And it also isn't responding quite as quickly. So that gets into the issue of the thermal mass that I was talking about earlier, and also the ability to respond quickly. And read accurately. Now, when you get right down here at the value, this says value, that's not right. Evidently, it didn't come through correctly in this version. But this is around minus 62, and there's a difference of about 3 degrees, which is kind of within the range of error on the sensors. And then you can see the altitude is about 42,000 feet. And it actually got warmer the higher you went, and then you kind of go through that cold spot in the thermal climb, and then you go on up towards landing. And then the internal temperature actually was the lowest on the way down, so it kind of went down and started back up again. Okay, so how do we measure altitude? The barometric altitude. Well, I did some checking around on barometric sensors, and I found one that is rated, to a fairly, well, you're going up to 100,000 feet, there's not a lot of air. Most of the things that people make for barometric sensors, not a lot of people flying high altitude balloons and stuff, so I don't know how big the market is for these. But I did find one that was rated between 10 millibars to 1,200 millibars, with like 1,000 millibars being sea level. And so I did a quick calculation. The pressure at 100,000 feet is 11 millibars, so that's right at the low end of what this guy can do. And I thought, well, that would be good. Some of the other ones I've seen, maybe they're good to about 40,000 feet or so. And I thought, okay, we're going to try this one. It's factory calibrated at 2 pressure points, but pretty close, but they're not anywhere near where we're flying. Okay. Now, converting between barometric pressure and altitude is not exactly an easy thing to do. I thought it was going to be easy. Shoot, it's just math, right? Well, yeah, it's just math. But you've got to correct for temperature. So the nice thing is the chip's got a temperature sensor in it. So, okay, you use temperature. And then there's a second order correction. There's one you need to do below 68 degrees F, which is mostly where we fly. And then there's one formula used below 36,000 feet, a different one for above 36,000 feet. And then I actually output the barometric pressure on the APR status string. So when this thing's coming down, if we lose GPS lock, it'll output the barometric pressure. So we can call the FAA up, who's real interested where the balloon is, or how high it is, because it's coming back through their airspace, they want to know. And so, we want to call them and be able to say, it's this higher, oh, it burst and it's on its way down, and sorry about that. We lost our GPS. Okay. I don't calibrate the barometric pressure before flight, like you would in an aircraft. You want to know exactly how high you are. This is close enough. When I've looked at the barometric pressure versus, you get your daily changes through the highs and lows coming through the barometric pressure changes. I'll see a difference of maybe 800 feet. That's good enough. We don't need to report altitude at 800 feet to the FAA. They're more interested in thousands of feet kind of thing, like 10,000 feet, 20,000 feet. Okay. So I ran the GPS altitude versus the barometric altitude and charted that, and you see it tracks pretty close. And then right up at the top, where you see the most, on this flight, we only saw 1,100 feet. I added the second order correction on the second flight, so this has only had one flight with some of the changes I made in the latest version, but boy, that's really close. And I don't suspect that it's always going to be that close. The first flight I saw a difference of 5,000 feet. Well, that's a lot, and that's when I added the second order correction and resolved that problem. And at altitude, it was only 15 feet off, which was unusual. Yeah.
For other systems and like for pilots and things like that, what is that delta expected to be? Is there any information on the net about kind of what averages for that?
The pilots in the group,
I don't understand the question. What is the average delta between GPS?
Yeah, Mark,
At 18,000 feet, you adjust your altimeter back to 29 or 9 or 2, so that you're not worried about what the pressure is on the ground. Every plane up there is all set at the same spot.
Okay.
So we neutralize above 18,000.
Yeah, you're separated by pressure altitude, not by absolute altitude.
Right.
and
It's pressure altitude.
I know at my house when I just set them both up, I'll see sometimes I'll see 800 feet, sometimes I'll see minus 800 feet, sometimes I'll see 0, sometimes it varies just depending on what the weather's doing.
But obviously the GPS is the most.
And it actually bounces around. Yeah.
Mark, the GPS altitude, the GPS is not optimized for altitude, so it's probably about 50 to 100 feet error on GPS altitude. Whereas circular on the for precision, it's more, 15 meters.
Yeah, and if you sit there and watch your GPS, you watch altitude, you'll see it do exactly what Tom said. It'll bounce up and down. It takes a while to settle in, but it never sticks on one.
So there's no true truth.
What is truth, right?
Generally, they didn't optimize it.
I use that same pressure sensor,
Uh-huh.
and it's one of the best that you can use for high altitude ballooning that's out there right now. There is one problem with it other than the corrections you have to do. It's almost impossible to hand solder it onto a board.
Exactly.
I have to reflow it with a heat gun and tin it first, and it'll melt onto it. But
Yeah.
you have to do some tricky stuff to solder it.
But the IMU is worse.
Oh, yeah.
Okay, next slide. All right, so we're going to talk about detecting burst. So I talked a little about this before. So here's the data of the accelerometer data of the second balloon. So right over here you see 1G, which is what you saw in the first animation, and this was 1G is just it's going up slowly. So what I've got here is I've got the AX, AY, and AZ, and then I've got the magnitude. So it's the sum of the square root of the sum of the squares. And so that gives me the magnitude. Magnitude is in green. So this green one over here, if you take the three of them, is actually overlaying the Z a little bit. But that's green, it's 1G. And then you can see right here, it bursts. And then it goes to 0 Gs for a little while. And then on the second flight, we saw this pulse. This almost 3.2 G pulse. And why it did that exactly, I don't know, but I think it may have to do with the shock of the burst being transmitted down through the flight string or something. And then there's a little period of time here that's free fall. And so I'm calling that less than 1 Gs for 1.5 seconds, or less than 0.2 Gs for about 0.8 of a second. So just by me taking and dropping this thing from the roof, I decided about 0.5 second at 0 Gs should be burst. And then it goes into its thing over here. And so that's been pretty effective. I actually put out a warble tone on burst, and 2 times now it's worked perfectly on burst. It'll come out with a burst tone long before we can see it on the GPS data. Just worked pretty well. Okay, now we're going to talk a little bit about the TNC and the radio part of it. Inside the payload that Nate just held up has 2 boards in there. There's a TNC board and there's the main board. And I showed you a picture of the main board earlier. It's got the sensors on it. That's the first board that I started out with, and then there's a battery. And I was talking about it being higher than the center. That's probably not the best place for it, but it's exciting, So I started out with the Argent Data Tracker 3 Mini. Maybe some of you have used that. I know that we fly a lot of Argent Data stuff, but I ran into a lot of issues with it. Because I was hooking it to a computer, most people just hook it and use it as some sort of a tracker or something, don't do anything with it complicated. And I was actually hooking it to this board and actually sending commands to it, and I was trying to get it to do a bunch of stuff. I ran into a bunch of issues. Contacted Scott, the guy that develops it, documented my issues and so forth, but he didn't really seem all that interested in fixing them. So he's got, I'm the only one doing this, I guess, and it's like, that's not how it works. It was also missing some would-be nice features for balloons. One of the main one was the ability to send a status string, have it save that, and transmit it right after an APRS string. So I wanted to be able to send out the APRS string with a lat long and altitude, and I want to send a status string that has the barometric altitude, the GPS information, the battery. I want those 2 sent sequentially, but not every time. So maybe every 3rd or 4th beacon would have that. And the only way he had to do that is to store that in flash memory. Okay, so I'm storing how many? Okay, once a minute I'm just rewriting the flash memory. Well, over a period of time, the flash memory is going to be history. And then, can't you store it in RAM? He said he didn't have enough RAM, so nobody else asked for it, so I didn't get that feature either. So I decided, okay, there's something else I need to do. So I decided to develop a customized TNC. And to do that, I incorporated the radio on the board. I was playing with the Bofang radios. I wanted a cheap radio, so I played with that. It was too big and too heavy. Put out too much power even on low. So I decided to start playing with these Chinese radios. I think a lot of us tried playing with these radios. also do software packet decoding and software DTMF decoding. So I'll go back to the main control board and show you that I have some stuff on there that I don't need anymore. Like a DTMF decoder I don't need anymore. The digipeater, SD card, and it has an optional GPS so I can fly it standalone. So the payload we're going to fly tomorrow is the other one over there. It's still pink, and it is just the single board version. So it's just the radio with the GPS on the single board version, not the dual board version. It doesn't have the temperature sensors, the IMU, or any of that stuff. And then it has a simple serial interface to the main board. So in this configuration, it just is a 3 wires between, actually 2 wires between the two because they have common ground. Okay, here's what that board looks like. So it uses this little radio, the 818B radio. There's a low-pass filter on here. I don't know how much you played with these, but they don't meet the FCC requirements for the second harmonic, so you can put RF filter on the output. This is the connector to go to the other board, the SD card. This is the spot for the optional GPS with the connector, processor, switching power supply down here, and some analog stuff over here. It's got 2 USB interfaces for it. I decided between the hosts to just go all USB. It's just so much simpler just to plug it in and have the thing work. So there's one GPS port just for the one port, just USB port just for the GPS, and one for the serial port into this processor. Okay. So the radios. I just want to talk a little bit about that Chinese radio a little bit. The nice thing is they're inexpensive. I don't know if you played with them, but they're about $12. Have to get them from China. Like I said, they don't meet the FCC requirements. They get really hot on high power. They'll run between 3.3 and 5 volts, but they get pretty hot on high power 5 volts. But if you run them, I'm running them on 3.3. On high power 3.3 puts out 500 milliwatts, which is nice. I haven't tried low power and 5 volts to know what that puts out. I know it puts out about 90 milliwatts on low, which isn't quite enough. The package is difficult to unsolder for the board if you have to change it out. I mean, it's this, just flip that one, Parker. You can see it's got this sort of weird connect. It's not really connected. There are pads on the back of the circuit board. You just solder this guy on, and then when you go to unsolder, it basically pulls the pads off the board, off the radio. Okay, not so good. But even prototyping, it's hard. You can try to solder wires to these things. It's just kind of a nasty package. Okay.
Mark? Get 5.
Sure.
Get 5.
5, okay. I mentioned that the TX ramps up slowly, so it kind of goes like that, rather than going on. So you need a longer preamble on your APRS data. The split RX-TX frequency doesn't work, and I'm working with the Chinese vendor to resolve that. Squelch opens up slowly, so I just run an open squelch. Didn't work okay. It's got some twist issues, and I'm worried about that with the 2 tones, though the high and low tones are not equal to each other, so I'm working on trying to figure some of that out. These are all the things that are on the main board that I discussed. This has a Bluetooth interface on it. That's the wireless part of it we're talking about, so I can actually, reprogram the payload call sign, slot times, those kinds of things, and just right before launch by connecting to the Bluetooth. The rest of it you can kind of go through is new blocks, the GPS is here. Some of this stuff, this is where the TNC went, and it's no longer there. And some of these parts, like the DTMF decoder, I don't need anymore. Okay. A couple things we found were interesting in post-processing. One of them is I created the KML file. This was done mainly for the students, so at 20,000 feet increments. I was able to annotate the temperature on here as well as the barometric pressure and so forth on the flight profile, which is kind of nice because you just go click and say what was the temperature here, what was the barometric pressure, as well as the lagging along. Then the other thing that we're referring to is if we take the GPS data and we plot it, we notice this very interesting thing. So over here is burst, comes down a little bit, and then this payload starts doing circles. And we've noticed on these long payloads, when you sit there and watch this thing, you see these payloads swinging around. It takes it. Everybody's nodding over here. You've seen the same thing, right? This was running about 7 seconds per Per rotation, yeah. And then it starts in, I should hold up what this altitude is when it started, but here's, I don't think there's enough air in the parachute to do much of anything. It starts getting it, and then as it goes down, that rotational period actually increases. Here you can, over here you can see it's got a small loop, so it's kind of going out to one side and going, you know, kind of like, it's kind of an interesting phenomenon.
Do you happen to know if that flight, whether you had a bunch of balloons on it?
I'm sorry?
Did you notice whether on that flight you had a bunch of balloons come back with you?
No. I don't think so.
That was a Gleeman?
The quick release.
No. We've just seen a lot of them and come back with these payloads swinging like that.
Right.
So,
Well, I've seen it do it worse when it has a balloon out there because they tend to rotate around the comet.
Okay.
Instead of,
Yeah, no.
so one of the things we fly, so the pictures you saw earlier of the Shards were from before we started flying a device that we call quick release, which is basically
right, yes.
On loss of positive lift, we try and separate the latex from the balloon string and send them different places.
Well, if you look on the EOSS Facebook page, when we started flying the 3 version, we didn't have 3 quick releases. So there's actually a video posted on there of one coming down about 15,000 feet with the balloon attached. And the balloon is actually circling around the top, so that may be why you get a larger amplitude.
Okay.
So if I look back at what I was trying to do versus what I actually did, except for the temperature, which I'm not quite happy with because we didn't measure it accurately on the way up, I was able to do everything I wanted to do. As well as I added a cut down. There's an external LED on the top, and it actually runs a fairly extensive self-test when it powers up. Checks it like is the GPS working, and all this stuff working. Is the SD card? Did the card fall out of the SD slot? Something like that. And then it sits there and it comes up, and then it'll wait for 3D lock. You know, it flashes red-green until it gets 3D locked and starts flashing green. So you have a pretty good idea this thing is working. You can also query it through DTMF codes and so forth. Let's see, we added the cut down, I mentioned that. I think that's pretty much it I had some Parker. So what am I going to do next? Well, I need to flight qualify the just the single board, which hopefully we'll do tomorrow. And then I need to get more flight time on these to make sure that this is proved to be reliable. It should be, but we don't know for sure. I need to do some refinements on the APRS decoding. I'm thinking of replacing the Chinese radio with maybe doing something on my own that's ambitious. Resolve the animation issues. And then compare some data over time. For instance, you saw that spike. We didn't see that spike on the first flight, but we saw it on the second flight. So is that repeatable? Is it not repeatable? Kind of thing. And then look at what other things can we do. You know, what else can we toss out there and so it'd be nice to be able to do. Okay. Thanks, everybody. If you have questions, you know, I'll be around.
I have a quick question.
Sure.
What kind of G loadings do you see on the way out? Just normal turbulence?
Just very, very small. I looked at the animation. I looked at the data. It's very small. Usually, they have the 1G with gravity. The rest of it are just kind of vibrating a little bit. It's like probably 0.2, 0.3, something like that.
Almost normal.
It's not. It is measurable, but it's
almost,
yeah. You could see it. You know, kind of. If we go back and look at that first animation right before burst, you can just see it. It's just from the rotation and so forth. But the interesting thing is when it's coming down the parachute, you can see it starts vibrating. It's rougher on the way down than it is on the way up because there's some of the vibration from the air on the parachute.
So, one of the things I'm interested in looking at is this is at the end of a flight string, a long ways away from where the authority is, either on ascent or descent. So we're pretty excited to get a flight qual so we can put it up top and see what it really is getting and looking like when it's right under the parachute, and from my view, in the blast zone, if you will, of the balloon breaking. Because I think we're going to see dramatically different stuff up there.
Than 70 feet below.
Yeah.
Another quick.
Sure.
Those Chinese radios are also available on the UHF band.
Mm-hmm.
Did you use Eagle to lay that board out?
No, I'm using Dip Trace.
Oh, okay.
Which is, I don't know, I thought it was easier to use. A friend recommended it. I started playing with it. It was easy to use, so I used Dip Trace.
I have an Eagle footprint for that Chinese radio if anybody is interested in Eagle. They designed an Eagle.
I did too. Yes, please.
Okay.
We have Kite too.
Okay, thanks everybody.
So, whoever